Okay, good morning, everyone. Today we'll finish up C amplifier, the final derivation, and then I want to do a brief overview and maybe an example of BJT analysis. So we'll go over a few things in preparation for the final. All right. Okay, question being asked, is the final going to be BJT? We can if you want to. All BJT problems? Is that what you meant? Oh, for the lab final. No, we'll talk about lab final separately. All right, let's see. So we stopped here on the input side. Let's go to the output side. All right, so output impedance ZO can be determined by setting V in equal to 0. So V in is equal to 0. From this, we can state that IB would be 0. And therefore, beta IB is also 0. Right? We want to eliminate as many variables as possible. So on the output side, we have IC. If we eliminate IB and reduce it to 0, we can eliminate IC from our equations. So we can find ZO. This is the impedance looking into the output terminals. And we obtain RC in parallel with RE in series with RO. Right? So if you're looking into here and determining impedance ZO, we see RC in parallel with RO plus RE. So if we have that, we can find VO. Right. So we can take the ratio. Yes. No, on the input side. Yeah, that's on the input side. So we can do that. There's also another simpler way. We can find VO over VIN simply by writing the expression for VO as the voltage across. What is VO? It's measured across RC. So it's voltage across RC. VRC gives us VO. And that's the simplest way. So if you want to make an approximation, remember at the beginning I said you can have multiple pathways you can derive. One is by finding the impedances and then taking the ratio of the impedances. The other way is if you write expressions by eliminating variables, we can write expressions for VO. And then in the equation for VO, we can incorporate VIN. Then we can take a ratio of VO over VIN. So anytime you're faced with any kind of circuit, different kinds of biasing circuits would result in different kinds of equations. But if you proceed with these steps, you'd be able to analyze and find the voltages, the currents, the voltage gain for the amplifier circuit. The reason I took this specific circuit as an example is because we performed this in the lab also, right? CE amplifier in the lab is the exact same circuit. What was the gain for the circuit in the lab? So let's see if we can get that. Obviously, we are not the ones. There have been greater minds that came before us who designed these circuits and determined that gain. We're just going to learn what steps they took. So if you wanted to find VO, I could write VO is VRC But because this is a small signal, meaning for AC analysis only, RC is connected to ground from the top, right? So the standard convention for VRC is that the top terminal, which was positive, is now connected to the negative end of VO. Again, go up to this step right here. All right. If I label this as X and I label this as Y, where is X and Y in this diagram? Is X at the top or at the bottom? So X is here, Y is here, right? So RC is flipped down. So the magnitude of VO and VRC remains the same, but the sign would be opposite because you are now measuring opposite polarity. And you can probably see where this is going. You have seen this graphically, right? You've seen this graphically when we did the graphical solution. So VRC is simply the ICRC drop. IC can be written as beta times IB. And IB gives us our V in. We can write an equation for IB is V in beta times RE. Plug that back in, substitute it in, and we can write VO is minus beta RC times V in or beta RE. Beta cancels out, you take V in on the other side, and you get VO over V in is approximately equal to minus RC over RE. Therefore, the gain of this circuit using the small signal analysis model is approximately equal to RC over RE. Okay. There are a couple of other ways also where we can determine the same thing, but this is one of the simplest and the easiest. Okay. Yes. You rearrange the terms, and R pi is much, much smaller than beta plus 1 times RE. So we can write IB in terms of V in from this step right here. Let's say beta is 50. 50 times 4,000 or 51 times 4,000 if RE is 4,000. So the question being asked is, first question that was being asked was how did we obtain V in, IB? And so it's basically by rearranging these terms. And the second question being asked was how and why we took beta plus 1 times RE as beta times RE. So beta is large enough so we can use an approximation. That was the answer. So usually we have to, 10 weeks or 9 weeks because we perform the lab in week 9, somewhere in the middle of week 9. So we have to get through a lot of stuff before we can, even perform the lab experiments. So we try to get through at least one sort of analysis, meaning we did the graphical analysis. Otherwise, if we had more time, we would do this before the lab as an explanation. Anyway, that's just spacing. This is not going to be on the final exam, but this is to show students how you can analyze a circuit using small signal model and determine determine the different parameters. All right, so that concludes all the material that is, that is part of the course. So we have the final exam coming up next week. Some of you have registered to take the exam on the optional Saturday timings. And so whoever is registered is approved. If you have registered for any of the other alternative times during the final week, meaning either Monday, Tuesday, Monday, Wednesday, or Friday with a different class or section, most of the requests are approved so far. It just depends on how many seats I have available in the classroom. Typically, it's never been a problem. At least 5 to 10 students from each section will take the exam on a Saturday, and that opens up space on Monday, Wednesday, and Friday. Okay. So I just want to do a brief recap of the course material. So let's go ahead and do that right now. And I believe I have something on the final exam page also. All right. Final exam. So again, please ensure that you read everything on this page. University scheduled exam is on the Friday. If you wish to take the exam earlier than Friday of next week, then you can choose any of the alternative options that are presented here. If you're taking it on a Saturday, you're pretty much approved. You can, just arrive on Saturday. I will accept requests until Friday afternoon. I will again post this on the final exam page also. So a student tells me submits a request on Friday afternoon saying that they want to take the exam on a Saturday, that's fine. I just need to know the enough numbers so I can prepare the exams and print them accordingly. If you do state that you want to take it on Saturday, but you change your mind at the last minute, that is also fine. Just let me know, okay, so that I don't have my count messed up. Yes. It's a written exam. Yeah. So final exam is all in person. There's no Zoom option. All final exams are in person. And because we had several students attending via Zoom, not in person, I will check IDs for everyone who comes into the classroom. Okay. So, I pretty much know most of the students by face, especially the ones who attend the class are there in my lab. So I know pretty much everyone, but we're checking IDs for some students. Hence, I have to check IDs for everyone. Excuse me. Let's see. That's for the dates. It's for 25% of your overall grade. Everything is pretty much from the quizzes, the homework, and the in-class solved material. There's no trick or twists to the questions, except, it might be something you've never seen before, but doesn't mean that you can't solve it. If you apply the steps correctly, and then you should be able to solve it. All right. So we had, first up, we had introduction to electronics and brief review of circuits, where we did Thevenin Norton circuit analysis. Obviously, those are not going to be assessed separately as a separate problem, but as part of another problem, you may be required to find a Thevenin equivalent, right? So everybody should be familiar with those concepts. Solid state electronics, short answer questions, maybe one problem, maybe two small problems. Diode and diode circuits, fundamental short answer questions, 1 to 2 problems based on the ideal diode analysis. and load line analysis. And then Zener diodes, again, short answer questions, one problem. Pretty much this would be a choice either between Zener voltage regulator or a load line analysis. I'm letting you know upfront. There's only two possibilities on the problem. There'll be either one of those. Yes. Okay. BJT short answer questions. 1 to 2 problems. FETs and MOSFETs, probably not a problem, just some fundamental short answer questions. So no problems from the FETs. Okay. And again, BJT amplifier, small signal analysis, again, fundamental short answer questions, no problem. So FETs, MOSFETs, chapter 5 and chapter 7, no problems except for fundamental concepts. And then it's open book, open notes, not open internet. Okay. If you have your notes and your course material, you can access it via the internet. But other than that, no other internet access. Meaning you can have your laptops, you can have your tablets, all of that is fine. If you wish to access the class notebook, if you wish to access the slides, if you wish to access your digital notes, that is fine. But access is limited only to course material, nothing outside of that. Yes. Yes. You can access the textbook. Yes. Yes. That would be part of the diodes. Yeah. Yes. Okay. So first question that was being asked was about how about rectifiers. So rectifier circuits would come under diodes, chapter 3. And the second one was about, can we simply show up if we request an alternative time? The answer is no, is because I'm going to update this page right at the top somewhere here. I will update the page saying that, okay, all requests for alternative times are approved, and I will have a date and timestamp. So if you submitted a request before that day and time, then it's approved. If you submit it afterwards, then you need to wait until I update it. Again, Saturday requests are all approved. If all students want to show up on a Saturday, that's fine. I mean, I can, there's plenty of rooms we can open up in building 20. And so, but so far, I believe it's about 20-25% of the class that has registered to come on Saturday, as of now. The students might change their mind later on, but I don't. Right now, it's about 20-25%.
No, I have a question.
So as I was saying, ideal diode analysis, rectifier circuits, wave shaping circuits, clippers, clampers. Just look at the fundamental ways on how diode conduction actually works. So let's go over that material.
Professor?
Yes.
Does the final like, are you assuming that the finals taking like the whole time period of the finals?
Question being asked is if the final will take about 3 hours or 2 hours and 50 minutes. Yes and no. It's up to each individual student. Typically, the earliest a student finishes up one of my exams for 306 was about an hour and a half or so. Some students stayed for the entire 3 hours, meaning 2 hours, 50 minutes. Most of the students were done between 2 and 2.5 hours. Does that answer your question?
Yeah, thank you.
Yeah. So again, it's up to each individual student. Average would be between 2 to 2.5.
Okay. I also have another question. So if you I was wondering if there's any space for the Wednesday class. Like I submitted one like a week ago or like a few days ago.
Yeah, so at the top of this final exam page, I will have a I will have a small note saying that all alternative requests are approved, and
Okay.
I'll have a date and timestamp on it.
Okay.
And
Sounds
so if a student has requested before that day and time, then their request was approved.
okay.
And
All right.
so I will update that probably not today, but tomorrow.
Okay. Thank you.
Yes. Yes. So the question being asked is if the request was not approved, then the only other time to take it would be the actual university scheduled time, which is Friday. Yes. And that's the actual university scheduled time. Okay. All right. Let's see. Review. All right. Chapter 1, we did Thevenin Norton. Not going to see anything with dependent sources, but the reason I like to do it at least for the first chapter is because, especially for the BJT, we have, we use the model where we have a dependent current source on the output side, right? So that's why we do that in chapter 1. But again, chapter 1 is not going to be assessed separately, but students as EEs, it's something that you will carry for the rest of your life, right? Fundamentals. All right, chapter 2, we had semiconductor fundamentals. So solid state electronics, basic fundamentals of what is classified as a conductor, insulator, semiconductor, properties of semiconductors. And then we had concepts in, let's see, in some problems based on these equations. So you should pretty much expect there'll be a problem based on these kind of equations. Okay. Intrinsic carrier density, drift current, mobility, velocity saturation. Again, fundamental concepts of how semiconductors are created. Okay, well, not semiconductors, sorry. Actual electronic devices are created from semiconductor materials, right? So basically doping process, how a p-type material is created, how an n-type material is created, what is a donor atom, acceptor atom, the p-n junction interface, what happens when it's forward bias, what happens when it's reverse bias, what happens when there is no bias, donor and acceptor concentration, charge carrier concentration equations. Again, concepts, thermal voltage, nothing on fabrication. Fabrication is not something I will assess or test. Leave that for EE 473. Perhaps next winter I might see some of you in that class. All right, diodes, very important chapter. Okay, so what happens at the junction? I think I already spoke about what happens at the junction, and then forward bias, reverse bias, and no bias. So there's the first portion of the chapter is basically the device physics of it, and then the latter portion is the circuit analysis portion, right? So the fundamental concepts the short answer questions will most likely be based on the first portion of this chapter, meaning the fundamental concepts. And then the analysis portion or the problems would be diode equation, and then let's go past all of this, diode circuit analysis, right? So we have 4 different models. I'm not going to ask you to do the iterative analysis, so probably not this, okay? So we have load line, ideal diode model, constant voltage drop. The ideal diode and constant voltage drop models are very similar, right? So I'll just go over that. Yes, Milan, you had a question? Yeah, I wouldn't ask about the iterative model, no. which is this, the mathematical model. All right, ideal diode model and the constant voltage drop model are exactly the same. If it's reverse bias, diodes are off. You replace it with an open circuit. If it's forward bias, then the ideal diode model states diode is a short circuit. You replace it with a wire. Diode is on, you replace it with a wire. And a constant voltage drop, you replace the diode with a constant voltage source, 0.7 volts. Okay. The problem will specify either 0.6 or 0.7. Okay. If it's a germanium diode and nothing is specified, you can make your own assumptions. Well, whether it's a germanium or silicon or any kind of diode. If nothing is specified in a problem, you make an assumption. Okay, and then solve the circuit that way. All right, so ideal diode analysis, we first assume a diode state based on the circuit conditions and the rules. If the anode has a higher potential than the cathode, then the diode is forward bias. It's on, replaced with a short circuit. If the anode has a lower potential than the cathode, then the diode is reverse bias, meaning it's off, replace it with an open circuit. So what happens if both anode and cathode are the same potential? We treat it as off, basically, whether it's ideal diode or constant voltage drop model. The anode must be higher than the cathode. If it's ideal diode, we ignore the voltage drop, but it still must be high. It could be higher by 1 volt, 0.1 volts, or 0.00001 volt, but the anode must be higher. If both of them are the same potential, then the potential difference is 0, meaning there is no bias, meaning a depletion region exists. So we treat it as off. So this question was asked in the class through the quarter, but I'm just clarifying it now. So if you see a problem and you see that the anode and cathode are the same potential, treat it as off. And then constant voltage drop would be exactly the same, except we now have a voltage source and forward bias of either 0.6 or 0.7 volts. All right. And then we did a comparison of the 4 multiple diode techniques. Depending on how many diodes we have, 2 raised to, so if n number of diodes in a circuit, we have 2 raised to n possible states. Right, so 3 diodes in the circuit, 8 possible states. We start with the assumption that makes the most sense, and then we analyze a circuit. If even one of the diode voltages is incorrect, then we have to go back and change the entire assumption. Okay, so in ideal diode analysis, if we make an assumption that the diode is on, then the voltage drop across the anode and cathode must be 0 volts, and the current must be in the forward direction. Okay, so again, here, let's state here. Basically this, right? If we assume that the diode is on, the diode is replaced with a short circuit, meaning the diode voltage VD must be 0 and diode current ID must have a positive value. If your results do not match up with your assumption, then your assumption is incorrect. If you assume reverse bias, then VD must be negative and current ID should be equal to 0. Okay, current ID should be equal to 0. So again, ideal diode analysis, when you make your assumptions and you solve the circuit, these conditions must be satisfied. So keep that in mind. All right, multiple diode analysis. I think went through this. This was a constant voltage drop model. And I said this was an excellent circuit because you had 2 raised to n, meaning 8 possible combinations. We started first with an incorrect assumption. Then based on the incorrect assumption, we made a second assumption. So we tested 2 states out of 8. There are 6 other possible combinations. So if you want to practice, this is a good problem. All right, then we had diode rectifier circuits, half-wave rectifier, full-wave rectifier. Problems on here would be very similar to what we did in class and on the homework assignment. Okay, so it'd be very straightforward in that sense. Full-wave bridge, and then Zener diode. As I said, either load line analysis, not piecewise, or a regulator problem. Okay. In the regulator problem, again, there are quite a few combinations that we can test. So again, it'll be either load line analysis or a voltage regulator problem for the Zener diode. Okay. Voltage regulator and diode clippers and clampers. All right, so all right, I'll make a decision right now. No clampers. Okay, no clampers on the final exam. But clippers is kind of an extension of the ideal diode model. Okay, and so clippers is something I might assess. So make sure you have your thorough understanding of ideal diode analysis and its application as a clipping circuit. All right, so that's for diodes. Then we had BJTs. In BJTs, again, we had concepts. Yes. No, I mean, the problem will state whether you use ideal diode, constant voltage drop, problem will state. It'll be given in the problem. If it's not given, you can assume or choose whatever you wish. All right, so BJT construction, again, fundamentals and concepts. Terminal currents, standard basic equations, Ford characteristics, reverse characteristics, transport model example, trying to determine the voltages and currents in a BJT. And then operating modes, determining the operating mode. That is, assume that's pretty much a given. Okay, determining the operating mode is pretty much a given. So 99% certain, a similar, that kind of problem will be on the final exam. And determining the operating mode basically requires us to determine the terminal voltages, the terminal currents. So as part of that problem, you might be required to find like IC, IE, IB, etc. Right. And then you should be familiar with the output characteristics, the regions of the regions in the characteristics, VBE, VCE, edge of saturation. Oh, edge of saturation shouldn't be. That should be 0.2. 0.2 or less. Okay, output characteristics, transfer characteristics. Then we had the forward active model. We had simplified equations for the forward active model, right, where we ignored certain parameters. There were a couple of examples for forward active. This was example 1, this is example 2. So make sure you have a thorough understanding of these example problems. Yes. Which one? No, it's a current source. It's a dependent current source. So right here in the center, you're asking about this? That's a dependent current source that indicates that the transistor is supplying a constant level of current at the collector terminal. So but that dependency is on the input side. It's either dependent on VBE or IB. It's convenient to take IB, so we just write it as a dependent current source beta IB. Okay, I get what you're saying now. Question being asked is there a diode for the base to collector junction? You tell me. What happens in forward active mode? You're gonna be assessed and examined right now. Wonderful. No, but this is for everyone. Okay, it's not just for one student. What happens in the what is required for forward active mode? Yeah, so base emitter junction is forward bias, hence it behaves like a diode. Hence, in the forward active model, we use a diode to illustrate the base emitter junction. Right? Makes sense to everyone? Right? This is the forward active mode. Forward active mode requires that first of all, if it's cut off, then the base emitter junction is reverse bias. If the base emitter junction is reverse bias, meaning VBE is less than 0.7, nothing's going to happen. It's not going to work. Right? It needs to be forward bias. Forward bias behaves exactly like a PN junction diode. Hence, we have that diode in there for the base emitter junction. Now, for saturation, the base collector junction is also forward bias. For forward active mode, the base collector junction is reverse bias. Right? So if it's reverse bias, the best model for it would be a dependent current source because a constant current is coming out of that collector terminal in forward active. Those flat curves, right? It's a flat curve, almost flat curve. Hence, we say it behaves like a constant current source. If it's forward bias saturation mode, we can put a diode in there, and that would work. But here it would be a reverse bias diode in place of that dependent current source. So again, the answer is yes, we could put a diode in there and show it's like reverse bias, but then that wouldn't describe the function of or the operation of our BJT. Does that make sense? Right? It is a PN junction, but it wouldn't describe what's happening at the output terminal. To best describe the output is a current source. All right, then we have short answer questions based on fundamentals and concepts. So there might be smaller problems based on these equations and these terms. Okay. Then you have the early voltage, operating mode determination. A couple of examples, biasing, voltage order bias. So CE amplifier and biasing circuits. So biasing, I'm not going to separately assess biasing circuits, okay? It's part of the problem itself. I mean, if we take a look at the circuit, we are using RC and RE to apply a bias to our BJT, right? So it's not as if I'm going to assess it separately, okay? But CE amplifier, no. So CE amplifier will not be assessed. Small signal analysis, understand the concepts, but I'm not going to assess it like separately, okay? All right, let's see. So we determine all BJT voltages and currents in here. There's 10 minutes left. Let's see, what else did I say was going to be on there? Yeah, FETs and JFETs, just basic fundamentals, short answer questions based on concepts. And chapter 7, again, just concepts, but I'm not going to have any problems or assess. Okay, draw a small signal model of this kind of circuit. I'm not going to ask that. Okay. And that itself is a lot. So also you have to keep in mind, I also have to set the exam and have to solve it. So I don't want to, usually we have to, so I have an exam on Monday, then a Wednesday, then a Friday, and we have to turn in the grades by Tuesday. So there's tons of gradings going on. So it's like pretty much working through the night for all of us. For BJT, let me just review, and there's another example problem that I had wanted to do. Now that we have, let's see, we have about 9 minutes left. So all right, just as a recap, let me just summarize in slide number, let's see, operating mode determination, like right here. Okay. As I just stated a few minutes ago, if it's forward active mode, base emitter junction is forward bias, so VBE is 0.7, right? So if you want to analyze a circuit, analysis steps, the first thing you want to check is what is VBE? What is the value of VBE, right? Because if VBE is 0.7, then cutoff is out. It's either active or saturation. But if VBE is less than 0.7, then it's cutoff. It cannot be active or saturation. So the first thing we want to check is what is the value of VBE. Yes. Question being asked is, can it be reverse active? Yes, that's a possibility. But again, it's not something I'm going to give an exam. It's just, we are just operating with the three in mind. Forward active, saturation, and cutoff. So one way to find VBE is if you have a circuit, let's say with resistors and some sort of biasing circuit, then you remove the BJT from the circuit and calculate what is the VBE open or open circuit. So if you remove the BJT, all you have is the base and the emitter, and you measure that voltage, right? So you'd have some sort of biasing voltage being applied to the base. You might have some sort of biasing voltage being applied to the emitter. In the previous example, we had -5 volts being applied to the emitter and the base was grounded. This example, where was the example? Where did we do that? Right here. We had -5 volts being applied to the emitter through the resistor, and the base is grounded. If you remove the BJT and measure between the base and the emitter terminals, I mean, where the BJT was connected, what do we have? VBE would be VB minus VE. So it would be 0 minus of -5. So VBE would be +5 volts. So VBE is +5 volts, greater than 0.7, meaning it's not cut off. It could be either active or saturation. So as a first step, you always want to check whether VBE is 0.7 or larger. So one way of doing that is removing the BJT from the circuit and just measuring at those terminals. So determine VBE when the BJT is open, when the circuit is open, meaning BJT is disconnected. And then, so if VBE at that point is less than, let's say, 0.6 volts, then it is in cutoff. Right? That leaves only active and saturation if it's larger than 0.7. So if then you check for VCE, if VCE is greater than 0.2 volts, then it's active. And if VCE is less than 0.2 volts, then it's saturation. Okay. And that's it. And then you have the standard equations. IC is beta IB. IE is IC plus IB. You have the conversions between alpha F and beta F. Alpha is beta over beta plus 1. Beta is alpha over 1 minus alpha. You will have access to all of those equations, right? So as a working practicing engineer, if you're sitting in a meeting, yes, you have to rely on your knowledge, but when you get back to your desk and you're doing calculations, you'll have all the tools you need. So again, use all the tools you need, show me your best work. But no searching the internet. Well, you won't be able to find the answers on the internet anyway. But no asking anybody for help. You can have your laptops, you can have your tablets. Access is restricted only to the course material. Yes. This one? This one? Yeah, the voltage source is 5 volts. No. So if you're given a circuit, there'll be some biasing on the circuit, right? If you give a BJT, there's some sort of bias being applied. Either the base, you're applying a base voltage, or the emitter is grounded, or you have a base voltage and an emitter voltage. Regardless of what the biasing circuit is, you want to check whether VBE is 0.7 or not. If VBE is less than 0.7, that means it's cut off. If VBE is larger than 0.7, then it's either active or saturation. And so one way of determining VBE is if you remove the BJT from the circuit and just calculate the base and the emitter voltages without the BJT in the circuit, you can find out whether it's, whether VBE on is like, larger than 0.7 or less than 0.7. That's all. Okay, as a reminder, course evaluations are open. So far, I believe, let me see, should have 13 of 37 students have submitted the evaluations. As a reminder, if you've forgotten, every student in the class will receive extra credit for doing this a little bit of extra work in proportion to the response rate. So right now, the response rate is 13 out of 37. I would say, but it's less than 30%. Yeah, less 33% approximately, right? So every student in the class receives 0.33 points of extra credit. So submit the evaluations if you wish. But whether you submit one or not, you will still receive the extra credit because your peers have submitted one. Okay. Again, I'll send a reminder email again, but the scale is, I think it's 1 to 5. And so 1 through 5, 3 is not average or neutral. 3 is not neutral. Okay. In the same way that if you want a 50%, 50% is not neutral or average grade, 50% would be a failing grade. So just letting you know, the scale is not, it's not a linear scale in that sense. Directly to your final grade. So if you end up with an 89.99 and extra credit is 0.3, bumps you up to 90 point something. Yes. So on Friday, no class. I'll be in my office and do an open office hours. Good question. All right. So we'll end class here today, and I will see you all perhaps Saturday, perhaps finals week. And for those of you in my lab classes, again, as I said, I send that email. And I don't know why it never came through. So it's weird. But this is what I had on there. What I'll do is I'll just make an announcement, make it easy. So I sent one earlier and then I just sent one again. It's not here. Hold on.